In this chapter, we will look at centripetal force and centrifugal force. We'll define centripetal acceleration and then calculate the centripetal force on a bicycle wheel. Acceleration times mass, of course, gives Newton's equation for force, but I'd like to notate when wheels rotate, they display an additional source. Recall that we are envisioning the rim being made of a bunch of keystone-shaped pieces that are being pulled inward. They, of course, are pulled inward by the tension on the spokes. If the spokes suddenly disappear, then this piece of the rim will fly off in a direction which is tangent to the rotation. When the wheel is spinning, there is a constant inward acceleration of the rim, the nipples, and the spokes, and there is an additional inward force from the spokes called a centripetal force. Sometimes the term centrifugal force is used, and this is really an incorrect term. Centrifugal force is really known in physics as a fictitious force that depends on a frame of reference, so forget centrifugal force and use centripetal force as the correct term. These lines represent the tension on the spokes in a non-moving or static situation. But when the wheel is spinning rapidly, then the tension will go up. Our instincts might tell us that it's probably not going to be much of a change, but we really don't know that unless we calculate the amount of the tension increase. Let's put some data in this box here. The bike is moving with a velocity of 20 miles per hour or 8.94 meters per second, which means that the linear velocity of the rim will also be 8.94 meters per second. This particular section here of our rim is going to fly off in this direction, and we have a bead seat diameter of 622 millimeters. The rim will have a radius of 311 millimeters or 0.311 meters. If the total mass of the rim is 480 grams and we have 16 sections, then each section will have a mass of 0.030 kilograms. We'll put the calculations in this box. The formula for the centripetal acceleration is v squared divided by r. My acceleration is therefore the velocity, which is 8.94 meters per second. I square that, divide by the radius, and I get my acceleration of 257 meters per second squared. The force is mass times acceleration, and when I multiply that out, I get 7.71 newtons, which is about 8 newtons. So if I start with a spoke tension of 1200 newtons, it's going to increase to about 1208, which is less than 1%. So I suspected that my increase in spoke tension would be pretty small, but now we have shown that it is. Now there is a force necessary to provide a centripetal acceleration of the nipple and the spoke itself, but that's going to be even smaller than the rim, so it's pretty negligible. But if we totally lose our minds and put this wheel on some type of a motorized drag racing bicycle and get it up to 200 miles an hour, then suddenly this 20 miles per hour here, that 200 miles an hour gives me a very large acceleration, centripetal acceleration, and my tension on the spokes goes up by an additional 771 newtons, which works out to about 64% increase in tension on the spokes. And that's not all, because at this very high rate of speed, suddenly the centripetal acceleration of the spokes and the nipples will start to become appreciable, and don't forget there's got to be a tire. So we're at the point probably where the rim would fail or the hub would fail, leading to a catastrophic crash. It's also possible under that scenario for the rather weak connection between the hook of the rim and the bead on the tire would not be able to keep the tire rotating with the wheel, and the tire would blow off, leading to a disaster as well. We obviously didn't spend very much time on this topic, and it's not really very important, but it is a force that applies, and it's not nothing, and I thought it was worth going into.